Thank you very much. My name is Roger Colbeck. I'm from the University of York, and I'm also part of the Quantum Communications Hub. And I'm going to tell you, maybe, I don't have very many answers in this talk, but I'm going to tell you a lot of problems, and I hope this will provide some fruitful discussion about how we can actually kind of complete this assurance process. I've focused on quantum random number generators, but other quantum technologies, quantum key distribution and things like this somehow fit as well. Okay, so what are we really trying to do? So imagine you get appointed to the, some kind of board, and you're supposed to come up with a procedure to certify random number generators. So you can imagine you go to the random number generator factory and you buy a random number generator, and you want a way to try to convince, well, not only yourself, but anyone who buys this, that this is really a random number generator. So you'd like to be able to produce some kind of stamp that you can put on this device and say, yes, this is really, really doing what I want it to do. Now, actually, I think it's very important, first of all, to be careful about what the stamp actually says, because we don't want to claim too much. And in particular, it's going to be very hard, I think, to really have a stamp that says, yes, with 100% certainty, this is going to generate random numbers. We should be a little bit cautious, because otherwise we could be embarrassed. So if we make too bold a claim and we put too much into our claim, then at some point we may find that actually it's not really working. If someone could come along and show that our claim was actually wrong, then we lose credibility. So we've got to be very careful. So one of the key questions is what should we really exactly try to say on our stamp? But before we do that, we should say, actually, what are we really trying to do? So what properties do I really want, ideally, from my random number generator? So in the absolute best case, what would I like? And there's two key requirements. One is that the outputs of this thing are uniformly distributed. But the other requirement, and this is for many applications very important, is that it's unpredictable by anybody else. Maybe for some applications you don't mind, but for a lot of applications, in particular cryptographic applications, we don't want other people to be able to guess our random numbers. You could almost, this is what we're really trying to do. And maybe just to say that the ability to offer the second thing is really what we can, is really what quantum mechanics is really helping us with. Okay, so we have a lot of tests, existing tests for random number generators, and most of them, or pretty much all of them, really just check that the outcomes are, well, they don't really certify that they're uniformly distributed, but there's a bunch of tests that if your random number generator is outputting uniformly distributed things, you would expect to pass, and we can check whether in fact that happens or not. But what we can hope to do from quantum mechanics is also try to also provide some kind of assurance that not only are these things uniform, but that nobody else can predict them. Okay, so the first thing is, well, checks on the outputs, if you only have one device, cannot give any assurance of unpredictability. So the second thing, you cannot, so the second requirement that's unpredictable by anybody else, you cannot get just by assessing the output. So no amount of statistical testing will do that. Very simple argument. So here's the inside of this random number generator factory. They've actually got a true random number generator, and they're using it to generate some random numbers. And the one they sell you just has a hard drive inside which has this list of random numbers stored on it. And when you buy that random number generator and start using it, it just outputs the list directly from the hard drive. Well, that means that somebody inside this laboratory could have a copy of those random numbers, and they're certainly not unpredictable by anybody else. Okay, so for any function that you might want to do on the outputs of your random number generator that accepts you'd like to have a function that accepts only if the random number generator is giving you random numbers by this definition such that no one else can predict them, but you certainly can't do that because by assumption these are true random numbers that no one else can predict, so they should accept, and these are ones that you're going to have to use. So they're going to accept as well. Okay. So what we do know is that actually if you have two devices, so now these devices aren't just the random number generators, but we're going to have two devices, and we're going to use the outputs of those devices to process those into random numbers. If we do that, then we actually can get this very good, almost probably as good as we could ever hope for, stamp that this output is random. Okay, and we've heard some talks about this today. This is called device independence, and I'm not going to go through all the details because that's a whole talk in itself, but the basic idea is you check that the behavior of these devices violates a Bell inequality. These lines represent a wall between them or some reason to believe that they can't talk to each other. They can't communicate, and if you make random inputs, then Bell's theorem basically says no adversary can know X. Okay, so we saw some things about this today. I'm not going to continue down this line, although I think this is actually the ultimate way to give assurance, because we've got to do this with things we can buy today. So at the moment, we can't, or you can't go out and buy a random number generator that does this, and it seems like it's going to be at least a few years away. But we'd like to use our random number generators now, so we'd like to still provide assurance. Okay, so this is one kind of maybe thing that we can hope for in the future, but for the moment, what are we going to do? Okay, and what we have to do is, of course, justify the randomness based somehow on the physics of the device. Okay, so now we're just buying this device. We're not allowed to use two. We can't just test the outputs of the device. So we're going to have to open it up and see what it's doing and base our assurance or this certificate on some kind of confidence of what it's doing. Okay, so there's a bit of overlap now in what I say and what we just heard in the previous talk. Okay, so here's my basic model of a quantum random number generator, or a basic schematic. Well, this is at least one way to do it. Okay, there's many different ways you can do it, but this is probably the simplest. So we just kind of take some source of photons, ideally single photons. We send them through a beam splitter, and if this detector clicks, we call it 0, and if this other detector clicks, we call it 1. Okay, and then what we have to do is, well, we have to say how much quantum randomness is in this. Okay, so this is where it gets a bit tricky, because you have to really be sure, you know, you don't want there to be classical randomness that you're accidentally using. You really want to know that you've got a quantum random number generator, otherwise you kind of lose all the advantages. So how do you know, when you set this up in your lab, that the reason that this detector, say, clicks and not this one is really because of, you know, there really was a single photon and it bounced this way in the beam splitter? How do you know it wasn't that there was some, I don't know, temperature fluctuation, whatever else, that made this one jump up and click? Okay, so you have to somehow do that, and then after that you have to do some classical processing to extract this. By this I mean just the quantum randomness. You want to somehow get rid of any classical randomness to give you your final output random string. Okay, so very schematically, the thing you have to do is estimate how much quantum randomness you've got and then run some randomness extractor. And I should just mention that there's this kind of framework, or a framework for doing this has actually already been put forward before a few years ago. Okay, oh yes, sorry, and I should say also that, yeah, one of the slightly annoying things about this random number generation is actually that we need randomness to do it. So to do this extraction, we're going to need some initial source of randomness. So really this random number generator is really an expander of random numbers. Okay, so let's now just unpack this estimate quantum randomness box. So it's very easy to put a box like this on the slide, but what actually do we have to do? Well, there's some real device. This is the device you buy from the manufacturer. Okay, and the first thing you've got to do is model this device. So you have to try to work out what this device is doing and come up with as good a possible physical model for that device as you can. Because whenever you really compute how much randomness is in a device, this is really, or how much randomness you get out, this is somehow a mathematical part. It's a mathematical property of your physical model. Okay, so all of the kind of difficult bit, or what I call the most difficult bit, is this step here. It's really to come up with the right model of your device. So if you buy this, or if someone sells you a random number generator and you want to know, is it really a random number generator, or how much randomness can I get from that, you've got to really take that apart. You've got to understand it in a lot of detail, or ideally in as much detail as possible. But of course, we can't ever model everything that's going on in a device, and maybe one of the real difficulties is knowing where to stop with your modeling, or at least trying to justify that you've not stopped at the wrong place. Okay, so why is this the most difficult part? Well, the physical model must be accurate. And what I just said before, it's really impossible to model everything. So how do you know that when you've come up with your physical model, it may describe some feature of the device very well. How do you know there's not some other feature of the device that you decided not to model that's actually really crucial for whether the outputs are random or not? Okay, so this is the last slide, so I'm going to just list somehow these are the questions or issues that I think need to be solved in all this. So like I said, I don't really have the answer to any of these questions, but I think that there are some very important questions here, and these are things for discussion. So the first thing is that this modeling, so suppose we actually do, and suppose we've actually got this procedure for providing this stamp for some kind of random number generator. Because it depends on this model, it's going to actually presumably depend in quite a particular way on the actual device that you've got. So one thing that would be nice would be to at least have what are the set of common principles that I can apply to an arbitrary random number generator as opposed to ones that are very specific. I don't really want to have a different procedure, completely new procedure for every single random number generator. I'd like to at least have some common principles, but I think we have to accept that some things are going to have to be tailored, and maybe it's just not, the common principles are at such a high level that actually it's really effectively at this experimental level very, very different procedures for everything. Okay, one is what should the manufacturer supply? So can they help you in this process? So the manufacturers also, of course, they want the assurance. They want to help you as much as possible. What can they do to make this procedure easier? This is probably the most important and most difficult question of all. When should we stop modeling? So this is what I was saying before. We have to stop somewhere. How do we know we've stopped in the right place? How do we know we're not missing crucial things? And this is also related to this question of why we shouldn't put too much on the certification stamp, or too big a claim, because we always have to stop somewhere. We can't model absolutely everything, and we need to be very aware that we could be getting things wrong. Okay, and are there better ways to construct devices, including different protocols, that can make this easier? Okay, so this is another thing that's worth thinking a lot about. So I showed you this beam splitter kind of idea for how to generate random numbers, but maybe that's not the best way. If we want to, maybe the manufacturers and we should all think together in order to come up with the right protocol such that it helps to make assurance easier. So these, inside this kind of category of questions include things like where you don't go for full device independence, but you can maybe try to make as much, you try to reduce the amount of assumptions that you make at all. So things like semi-device independent approaches that we heard earlier today are certainly a way to do that. Okay, so that's what I have to say. So I don't really have any answers to these questions, but I hope these provide some kind of things to spark discussions later. So thank you.